Hello, and thank you for checking out my video on machine learning and how to write machine learning code in Python. In today's video, we're going to be talking about classification algorithms. Now, classification problems are the most fundamental problems we are going to encounter in our everyday life, in working with data even, and they're just essentially yes or no questions. True or false, 0 or 1 in computer speak. A great example of this and how we interact with this in our daily lives is email. When someone sends you an email, your email is actually processing with a classification algorithm whether that email gets sent to your regular inbox or your spam folder. That's a classification algorithm that we didn't even know. It's happening to us all the time. Decisions are being made for us. That's essentially what we are going to implement on our data set here today. But I just want to touch briefly on how these generally work and what we'll be using. So we're going to use a decision tree and a support vector machine. And a decision tree it's been around for a long time. I will show you and visualize how it works, and we can see it's the kind of process that it takes. Support vector machines is a little bit more mathy, and I will try to explain it to you the best I can. But essentially what we're going to do is we're going to split our data and group it into a test and train set. We're going to implement these packages, and we're going to run our data through it and then see how they perform, and then we'll compare these two different algorithms against each other. So let's jump over to our Jupyter Notebook. Now, I've created this and I've made it available on my GitHub page. I will post the link to that in the video description. Please go ahead and check that out. Follow along. Use that as a guide, as a reference. By all means, it is there for your use. So please make use of it. Okay, so we should be all familiar with these packages. If not, I have videos on all these packages, so please go and check those out. Let's shift enter to run those and import all those packages into our Jupyter Notebook. We're getting all those tools from our toolbox and putting them on our tool bench. Okay, so now let's load the Titanic data set. We've seen this before in my data exploration video. We're just going to pull that down from the Seaborn package because Seaborn has that data set available for us. Thank you, Seaborn. And what we see here is we're going to print out the shape. It's 891 rows and 15 columns. We're going to get the info on all those columns, and we're going to see what type of data it is, how full that data set is, and what are the column headers there. And as we see, we're missing just a little bit of data. What we're going to do here is we're going to create a list of all the attributes that are missing data, and then we're going to get a sum. We're going to get a count of how many pieces of missing data there actually are. So shift enter to run that, and what we have here is a list. There are 4 columns and the respective amount of missing data. So no biggie on 2 from embarked and embarked town. We can make do with age there, but we're going to drop deck. That is the majority of the data set. We're missing it, so let's just get deck out of the way there. So we're going to drop deck altogether from our data set. So see ya. Adios, deck. Okay, age. Age had 177 missing values. What we're going to do is we're going to use pandas interpolate, and that is going to use the context clues from within the data set and use the surrounding data to impute some data there. It's not going to change our min or max. Actually, it shouldn't. I've done this a number of times, and it has not changed the min or max, and it's only changed the average just by a little bit, which we would expect it to do. But it's not going to make any crazy. It's not going to do anything crazy to our data set. Now we have a full data set minus these 2 here. So embarked and embarked town. And just by looking at the data set and what those represent, it seems like they're tied to each other. So they seem to be dependent on each other. So let's see if we can impute the data based on what's there. So we're going to run this to pull all the null rows with null values. And so what we see here, unfortunately, those values are missing from the same two columns, so we can't use one to impute another. So all I did here in this lower block here is I just got the mode, so the most common item. So Southampton, which actually stands for S for embarked town. Southampton, by far, that's the most. That's where people got on the Titanic the most. So we're just going to impute those, and we're just going to fill those null values with Southampton and S, respectively. Okay, so let's just take a look here and see how many columns have null values. Every single column has a value now. So that's a crash course on pre-processing. I have a whole video on that, so please do check that out. And sorry if we ran quickly on that. Okay. Another thing is machine learning algorithms. They do not like string values, and there's a way Pandas has a method called getDummies where we can turn string values into integers. We're not going to do that here. We're just going to run with the integers, the floats, and the booleans that we have, and we're just going to drop all the string values for the time being. And we can talk about that later. But in order for simplicity's sake, let's just remove all the strings, all the columns that have string values from our data set. And so that's sex, embarked, who, embarked, town, alive, and class. So, and we're going to drop that from our column. So Shift Enter to run that. And now all we're left with are columns that are just integers, floats, and booleans. So, and booleans are true, false. Okay, so now we can get into running and implementing our decision tree. And so we'll need to import that from sklearn as another package we haven't talked about yet, but it's a fantastic package that we can pull just from Jupyter Notebooks here when you downloaded Anaconda. That also pulls in. So that is what we're going to use to run our decision tree. And this train test split, that is crucial. That is going to allow us to split we have this like one main data set, 891 values of now I believe 9 or 10 columns. And we're going to split that data set into we're going to train our model, and then we're going to test our model. And I'll show you what that means here in a second. But for now, let's run this code, and then we're going to create an X and a Y. So we're going to hide our classification, what we're trying to predict, is whether a passenger survived or did not survive. And we're going to use the data surrounding. That's going to be our answer key, and we're going to use the data surrounding that to allow our model to predict whether a passenger survived or died. And so we're going to use this X here, which is going to represent our data, and we're going to hide whether or not we know that passenger survived. And then Y here is just going to be the answer key. And so let's run that. And then here, the train test split, this is where that comes into play. And so now with this X and Y, we're going to run X train X test, Y train Y test. So now we're going to train our model with all the X train and the Y train. And so our model is going to look at all of the entire data set minus the answer key, and then match up the answer key to it with a train set. And then the testing set is what we're going to look at a little bit later. And the test size here, 0.3, so we're going to use 30% to test later. We're going to train the model on 70%. We can move that to whatever we want. If we want to do 20%, So that the smaller this number is, the more data we're going to allow our algorithm to learn from, which the more the better. So I bet if we did a test size of 99, so we allowed we trained our model with nearly all the data, this is going to give us a great answer. But we want to give our model a lot of data to learn from, but we also want to see how it performs. So we'll use the test size. We're going to test it with 25% of our data. So it's going to learn from 75 and we'll test 25. And then this is really important, classifier, decision tree classifier, and we're going to fit the X and Y train. And then we want to predict the Y. We want to predict the Y predict is going to be the X test. Okay, and so what this is here, then now we want to we have run our algorithm. So it's tested it, it's predicted it, it's done that all behind the scenes. We don't have any, we can't see it. It's done it for us already. So in order for us to understand what has gone on, we want to print a confusion matrix, and that's going to show us the true positives, the false positives, the true negatives, the false negatives, and how our machine learning algorithm actually performed. So from sklearn metrics, we want to get the confusion matrix, and so Shift Enter to get our confusion matrix. And what we have here is this is our confusion matrix here, and so this is our test data, and we see 105 predicted accurately and 62 predicted accurately. So what we're looking at there is the upper left and upper right. So the upper left and the bottom right. The upper left, this 105, are the true negatives. So this is what our algorithm has actually tested and run through, and it has actually said, yes, these people did in fact die. Based on all the data, it predicted 105 people died, and it was right on those 105 people. True positive, these people survived, and our algorithm proved that those people actually did survive. However, the upper right and the bottom left, they predicted it wrong. So it predicted these 32 people died when they actually did not. They actually survived. And then it's predicting these people did die, or these people did survive, but in reality they actually did not. And so what we have there is that's going to be our basic understanding of how our model is performing. And what this is doing here is showing us a larger layout. And people normally are attracted to this accuracy score. It's 75% accurate. Okay, and you want to definitely take that into consideration, and that's a good rule of thumb to definitely look at your accuracy. How is your model overall performing? And where 75% accuracy without doing much pre-processing, that's actually pretty good. We did very little in order to get our model up and running, and to get that's much better than just flipping a coin and seeing and saying whether or not somebody lived or survived or lived or died on our with this data set. And so, but what precision and recall, we definitely want to always take a look. And the F1 score is like a hybrid of precision and recall. But precision and recall, and what precision is doing, it's taking our true positives and false positives, and it's what what the precision does is takes a look at the total predicted positives and showing how well it does. And then the recall is looking at the actual positives and seeing how well it's performed based on the actual positives of the predicted, or not of the predicted data set. So I hope that makes sense. If it doesn't, accuracy, definitely rule of thumb. Precision and recall are a little bit more fine-tuned ways of understanding how our model is performing. But I hope that is a good teaser for what a decision tree does. Another thing we can do is take a look and see how, kind of see the inner workings of what that decision tree is actually doing and how it functions. This is kind of a bunch of gobbledygook of the math behind it. I'm not really concerned about that. What I am concerned about, though, is something that is not done running yet, is the actual tree. And so this is the actual tree, and this is what is going on behind the scenes, is making decisions, and it's making these yes or no decisions. It's classifying our data, and it's making a ton of decisions based on all of our data, and based on all of these decisions, we're splitting the data into a yes or no. And so we have leafs and nodes, and we have a leaf, and we have a node, and it's just breaking it up. It's breaking up all the decisions and breaking it down onto until the algorithm makes a final decision on whether or not someone has survived or died, or is a 0 or a 1, essentially. And that's what is going on behind the scenes. There are other visualizations we can import into our Jupyter Notebook to get a better look at this, but this is a general understanding of what's actually occurring behind the scenes. So I think that's very, very fascinating, very cool. And that's essentially what a decision tree is. That's how we run those. Those are the basic understanding and inner workings of how decision trees are run, and what we're looking at when we're getting the accuracy scores or the recall or the precision scores for that. SVM, somewhat similar. It's a more complex algorithm that's gonna plot our data and then seek to run like a linear regression almost, run like a regression line, but it's going to be a very optimized regression line. And it's almost guaranteed to give us a better accuracy score, an overall score, than what our decision tree has done. And it's going to draw a line between the two types of passengers, those who have died and those who survived. So because we've already split our data, most of the work is already done. We just, at this point, have to import SVM from sklearn, and we just name that yPredict again as from the X test, which we've already created. We just have to call it the SV classifier, and then we can run that confusion matrix once again. And now we see we have a our accuracy rate increased by 3%, and our overall precision and recall they've both increased, and we just see better results altogether from our. We're looking at our true negatives and true positives. So this is how good our model is doing. So it's predicted that these people it's predicted right on how many people have died and right how many people have survived. And then same here. How many people so the inverse, how many people had the model has, it's a false positive, how many people have died, but the model's predicting that they've survived, and then a false negative, it's predicting, which is that's actually worse. We don't want to, for a lot of medical studies or something, we want to see much less false negatives. It's predicting that somebody died. It's predicting somebody died when in fact it's predicting somebody survived when in fact they died, is what that number is representing. Okay, so I hope you get a good understanding for how to run a decision tree and run an SVM. And these are excellent packages from sklearn that really reduce the amount of code that we have to run in order to get these results and to see how a model is going to perform on a set of data. Lastly, bonus algorithm, KNN. This is a nice, easy one. It doesn't actually work all that well for this specific data set, because it's clustering. Think of your Spotify or your Netflix referrals. If you like this artist or you like this show, you're more likely to watch this show or listen to these artists. It's a clustering of things, which we only have 2 clusters, those who survived and those who died. So it's not gonna. It will probably be the least accurate among the 3 algorithms, but nevertheless a very cool and good algorithm to know and learn. And since we've already done our pre-processing and we've split our data already, it's very easy. The sklearn makes it very easy to import these packages and then just run a set of code to run these different algorithms. And so yeah, what we've predicted so far, yeah, it's running. So if you don't remember, 75% accuracy is what our decision tree is predicted. 78% is what SVM is predicted, and now we're only here at 70 with the KNN, which, I mean, not terrible, but it's underperformed the other 2 algorithms. And what this is doing is it's classifying. It's going to plot and then think of like a scatter plot that has 2 different colored dots, and it's classifying that one dot is blue and the other is yellow or something, and just clustering based on like a scatter plot. And we can see here again our true negatives and our true positives, which it's not doing a very good job on classifying our false negatives here. It's underperforming there significantly. Only a 37% rate on our false negatives. So that is what I have. We've run through some pre-processing, running a decision tree in SVM and a KNN algorithm. I hope this is helpful. Let me know what your thoughts are. If you want to see other more detail, or you have any questions, I'd be happy to answer any of that for you. Feel free to reach out, and definitely check out this on my GitHub page, which will be listed in the description of the video below. All right, thanks so much.